guys, and welcome back to our channel. Today we're going to be reviewing some of the middle school problems from TrinMac Virtual Winter 2020. If you want to see all the problems, they'll be linked below. If you have any questions at all, please comment below and we'll be sure to respond to them. And if you like this video, please subscribe. All right, let's get in.
Let us get started. So we're going to warm up with one of our user problems. This was problem 1, just a warm up. I don't think we'll need too much time for this, but I do have an interesting observation to point out about this problem. But just take 1 or 2 minutes, and then once you have an answer, feel free to just say in the chat, and I'll be checking that. It seems like most people are getting the right answer. Okay. Yes, so 256 is the right answer. And so this is very interesting. So some person put what they said, like what the values for each variable were. And so let me walk you through the 2 solutions to this problem. So one solution is kind of to realize that it's kind of like the competition strategy solution, where you kind of realize, okay, 12x plus 8y equals 16 is a line, right? So in the xy plane, right, this is a line. There are many different x and y solutions to this problem, right? So this is some line over here. I'm not sure if this is exactly the slope. I think it's actually negative, but regardless, right? Like there are so many x and y points here, but somehow the problem's telling you that for all of these possible x and y values, they're asking you to find 64 to the x times 16 to the y. That must mean that all of these x and y values all generate the same solution, because otherwise this problem can't work, right? Like if one solution for x and y is 1, 2, and the next one is 4, 5, right? They can't both work for, they can't both generate the same solution for 64 to the x times 16 to the y unless they're the same exact solution. Because of that, the easiest way to do this problem is just to say, oh, okay, if x equals 1, y is going to be equal to half. So then I just do 64 to the 1, 64 times 16 to half, which is the square root of 16. This is 64 times 4, 256, right? That's like the fastest way, I think, competition wise. And it's like, it's like not as legitimate, but when you're doing competitions and you're trying to save time, it's, the strategy is not to have the most legitimate solution. It's just to get the right answer. But the most educational thing to do here is still going to be to show you how to do, the actual solution. I'm sure a lot of you did this, so I would just go through it quickly. You have this original equation, 12x plus 8y equals 16. Let's just divide. Well, actually, why don't I just, right, we have our solution right here. So you read this here. What the strategy is basically, first we divide both sides of the equation by 2. We notice that we can express 64 to the x and 16 to the y as a power of 2, since they're both, powers of 2. So 64 to the x is 2 to the 6x. 16 to the y is 2 to the 4y. And then if you're multiplying those things by the same basis rule, right? Like if you have 2 to the 3 times 2 to the 2, that's the same thing as saying 2 to the 5. You can add those powers, right? So here what we have is 2 to the 6x plus 2 to the 4y is this step right here, right? 2 to the 6x plus 2 to the plus 4y. And what's perfect about that is that we just got this equation right here that says 6x plus 4y equals 8. And that's from dividing the first equation here by 2. And all of a sudden we're done, right? Because then we just know it's 2 to the 8, which is 256. So that's a more legitimate way of doing it. And this kind of shows how no matter what x and y I have, I must get the same answer, 256, right? But the strategy that you can learn from this is that, you see this problem where it's asking for a product. A really common strategy is to find ways to get things in common with each other, right? So usually that's going to be like common denominator, but here is going to be the common base, right? So we want to express these things as like 2 to the whatever, and then by doing that, we were able to combine them into one term, 2 to the 6x plus 4y, right? And like in similar problems, if you see like 27, you see like 27 to the 2 times 81 to the 4, it's almost always going to be easier if you just express these as powers of 3, right? So this would be, so 27 to the 2 would be 3 to the 6, and 81 to the 4 is just going to be 3 to the 16. And that would just make your life easier, right? Like now you immediately see this is 3 to the 19, as opposed to like for example, multiplying this out, which would take forever and would just be unnecessary, right? So, those are, I think, the strategies to learn from this problem. But overall, I think most of you got it. Whichever strategy you use would work. Let's move on. Problem A. So this is a good one, and I think there's a really interesting strategy for this one that will be very useful. Okay, I think I can talk about strategy now. So when you see, this huge mix of square roots, right? Like the thing you don't want to do is like stare at it and try to actually compute values. Because the thing is, it goes on infinitely, right? So you're going to have to keep on like calculating 12 plus square root of 12 plus square root of 12, and you're never going to be able to like actually like really like intuit what the value is. The best way to do this though is to make use of the fact that it's an infinite value, that it's an infinite, that it keeps on going, right? So here, what you'll notice is that this thing right here is technically the same thing as this larger part, right? What's it like if I ask you what's the difference, it's really hard to tell because this is an infinite number of 12s and this is an infinite number of 12s. So how we use that is that if we call this larger thing x, this is actually also x. So that's what makes this problem really interesting, right? So if we just set this whole thing equal to x, right? Now we have a new equation, which is that the square root of 12 plus x, 12 plus x is equal to x. So this is a really important concept, and this is like essential to understanding this problem. The key part of this problem is that it's an infinitely, like the terms are like infinite, right? Like it just keeps on going and keeps on repeating itself. So there is no difference between what I'm highlighting here, right, in pink, and the larger expression. Because like let's just zoom out a bit. Let's just take out this pink part, right? If we take out this pink part, all it is the same thing as the bigger thing, right? Like if we take out this pink part, what is it? It's going to be square root of 12 plus another square root. Oh, shoot. Oops. Plus another square root. And then it keeps on going, right? That's the same exact definition as our original larger term, right? And so what happens when you have these infinite series is that you're able to kind of logically say, okay, nested within this larger term is the term itself, right? So if we call this larger term equal to x, right? If we say this is equal to x, then we can also say that this is equal to x. And equivalently, the same logic goes that we can say that this is equal to x.
I'm seeing a lot of questions that are like, well, why are they not different? It's just the fact that because this sequence goes on forever and ever and ever, it seems like, yeah, the inner x should be less than the outer x, but since they both go on forever and there's no endpoint, they're actually the same, which is the really, really cool thing about this problem.
And so I know this is a really like weird concept that you haven't seen it before, but I also assure you that this is like very unique to this kind of structure. Like I don't think any other problem has this kind of thing where you have like a smaller value nested within itself. It's kind of weird. But once you can like try and kind of believe this setup, then you can do any of these similar problems going forward. So we have this expression here now, right? Square root of 12 plus x. And so once we square this, we get 12 plus x equals x squared, right? And now we're just solving a quadratic. I think we all know how to do that. So this just factors into x minus 4 times x plus 3 equals 0. And can someone tell me in the chat why the solution is 4 but not -3 in some responses. I think the easiest way for us to see why it's not -3 is to look back at the problem, right? If you think about this sum a little bit, it can't possibly be a negative number because first of all, you're taking a square root, right? The square root of something has to be a positive number. Okay, great. Let us move on. And here's the solution for that, what we just explored. And we can send these out afterwards. So if you want to look at it again, feel free to. Okay, here we have a problem honoring our Captain Akash. This is a geometry problem, so different from what we've done so far. Take a few minutes. What I always recommend doing with geometry problems is to, before you do any work at all, kind of develop like a roadmap, like kind of think about what lengths do I need, what angles do I need, what shapes do I want, and think about, how am I ultimately going to get to the solution, right? Because some of these geometry problems aren't going to let you, get certain like lengths and areas, or it might be way too hard, right? So you really want to make sure you have that plan first before you spend a lot of time, putting in the work to find those lengths and angle calculations, right? Because then you're just wasting that time. So just make sure you are, developing a strong outline for how you want to tackle this problem and then tackle it. And there are multiple ways to do this problem, of course, as there are with basically any geometry problem. All right, so let's get talking about some possible strategies. So does anyone want to share in the chat if they have any, if you can tell me what sides you might have used to form like a triangle, or what shapes do you use? Like, did you use A1H? Did you use A1S, A1K? Curious. You assign a point X to the midpoint of side A1H. Yes. That is definitely a cool strat. Yep. Okay. A1S, A2 is a right triangle. Yes, that is also a great observation. Yep. It looks like, yeah. So the reason why I asked is, to show that there are many different ways you can get to the solution of this problem. Right. So as I said before, you really want to outline first, what shapes do I need, right? And to make sure you can get those values, right? So let's first look at this triangle right here. That was poorly drawn. Oh, why am I not end? Oh, perfect. There we go. So let's look at this triangle here, right? What is so cool about this triangle? Oh, so this triangle, let me just make this clear. It's A1, S, A2. And then we just said that this was A1S. So from here to here, this length is going to be 4 root 2, because the lengths of the legs of the triangle are 4, or each 4, so this is going to be 4 root 2. And then here, what you have to notice is that when you draw this midline, this is 2 because it's half of the square's length. This is also 2 because of what we said before about these lengths all being the same, and this is 2 root 2. Right. So now once we do the Pythagorean theorem with 4 root 2 and 2 root 2, we get, here we have 32, here we have 8. Add those up, you get 40, and you get 2 root 10 when you square root 40. So good job to all those people who did it. But the key thing about this problem is not that you know how to do all the calculations correctly, is that you know that you want to have that outline before you really get into any of the geometry problems, and that will really make sure that you're not wasting any time on solutions that aren't going to work out eventually. Okay. Great. Let us move on once more. Oh shoot, I think we might not have time. Okay, very quickly. just look at it for like 30 seconds and I'm going to explain the solution. Because I think once I say the solution, I think, the learning out of this, the educational value out of this problem comes a lot from the solution. And like, what I was saying before about really outlining the way you're going to tackle the problem is actually relevant for almost like basically any problem. And like everyone basically does it in their head, or they probably do it too quickly and then they try to dive into calculations. But especially for the geometry problems, that's when you really want to make sure you're outlining your strategy before you really get into calculations. So in this problem, also pretty relevant. So it seems like most people should have been able to take a look and to see if they just like understand what the problem's asking. So let me just dive right into the solution. So whenever you see these problems about cubes dividing or anything dividing a like factorial, the best thing to do is not to actually calculate the factorial. Because think about how much time that's going to take you to calculate 9 factorial times 8 factorial times 7 factorial. That's like, 1,000, that's into millions or maybe in the billions, right? Like that's going to be a huge number and it's going to be really hard. Does everyone here know about prime factorization? People heard about that? So like if I wanted to prime factorize 6, can someone just put in the chat how to prime factorize 6? Perfect. Okay. Yep. Same strategy here, right? We have a super big number. We want to turn it into a bunch of like smaller prime factors that we can easily manipulate, right? So here, if you actually had time to do the problem, what you would have done is you would have turned this into prime factorization, which is 2 to the 28, 3 to the 12, 5 to the 5, and 7 to the 7 cubed. And you would have just done that by looking at each factorial, right? It's like 4 times 3 times 2, right? So 4 gives me 2 powers of 2, 3 is 1 power of 3, 2 is 1 power of 2. So just keep keep a tally of those prime powers. You look at 5, that's obviously 1 power of 5. 6 we just did. 5 factorial is 1 power of 5, and then you get all the same powers that you just did with 4 factorial, right? Just 5 times 4 factorial. And so once you do that work, you get this prime factorization. And what you need to do is you say, okay, in order for a perfect cube to divide this, right, that cube, when it's prime factorized, cannot be like 2 to the 14 or 2 to the 17, because you cannot have a perfect cube of 2 to the 17, right? Because the power is not a multiple of 3. But if I had 2 to the 3 or 2 to the 9, right, then the perfect cube of that is going to be 2 to the 1 or 2 to the 3, right? So you need to make sure that the power of each prime factor is going to be a multiple of 3. And so because of that, the simple way to do this problem is just to look at each power of each prime, look at how many of its powers could be multiples of 3, as shown in the solution, and then multiply all of those numbers and to get your final answer, right? So like, for example, for 2 to 28, we see that the multiples of 3 are from 0 to 27. So 0, 3, 6, 9, 12, blah, 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 to 27. There's going to be, I think, 10 of these, which means that, yeah, as you can see here, when we do our final multiplication, 2